Welcome, bienvenidos, buenos dias. Today we're going to be talking about an Edge KV store built with Wasm Components. First off, who are we? My name is Ben. I'm a software engineer on the storage products team at Fastly.
And I'm Dan, and I'm a software engineer at the Wasm team at Fastly.
First off, some background. What is a KV store? If you don't know, you can think of a KV store as cloud storage for your hash map. You send us keys and values, and Fastly stores them and globally distributes them. We can have a look at our HTTP API here. If you've used anything like object storage or another KV store system, this is going to look pretty familiar. We basically just have a CRUD API where you can create, read, insert, and delete. Here's a couple curl requests that you can see where I'm inserting a key, reading it, and then deleting it. You can also do this via our compute platform using our Rust SDK, JavaScript SDK, or Go SDK. The code's going to read pretty similar. We open the store, insert a value, read the value, delete the value. But what's an Edge KV store? If a KV store is cloud storage for your hash map, an Edge KV store is a CDN for your cloud stored hash map. You can see this in action on the right-hand side with these cache headers on the curl requests. So on this first lookup, we get a miss, a cache miss, even though it is returning the value. And on the second lookup, we get a cache hit. So that means that the node that you're reaching out to has read this value before and stored it in the cache. That second value is going to be about 2 to 5 times faster to read, depending on your internet connection. We also store 404s down here in the cache. After we've deleted, you can see that the first lookup, again, cache miss. Second lookup, a cache hit. And behind that, today's infrastructure, if you make an HTTP request from the open internet, you hit api.fastly.com, your request gets routed to our KV store compute app. This is actually a Wasm payload running on Fastly's compute platform. The KV store does validation of your request. It performs all the caching operations, shielding, authentication, and so on. Because this is where the caching is handled, if your data is cached in here already and you're just doing a simple lookup, your response gets served out of here immediately and your round trip is done. If your data isn't cached or you're performing something that needs to touch the durable storage, like an update of a value or deleting that value, it gets sent to our storage routing system, which is another compute app, and finally to our durable storage. The other way of using it is, again, via our compute applications and building your own compute application. Your request comes from the open internet again, this time through your Fastly provisioned domain name. Once your app takes over, you craft your KV store request using the SDK that we saw before. And that gets passed over the Wasm API to our host platform, which turns it into an HTTP request and sends it onto the KV store like normal. Dan's going to talk a bit later about, or right now rather, about the host platform.
So when you look at how we implement a feature like this, one of the obvious ways to do it is to add the feature to the host platform. And just add it to the native code that we have in our host platform and allow user applications to talk to it through the public API. This works. But as we look at the feature, we expect the KV store to be the first of many features we're going to implement in this platform. And so we don't want to have all these features living inside our host platform. That means that they're living outside of the WebAssembly sandbox, so they're not sandboxed. And it means that the host feature has to be, the platform features have to be somewhat more integrated with the host platform. We can't iterate rapidly with them because they have to be tied and linked into the host platform. So we'd like to figure out a way to have the platform feature run inside the WebAssembly sandbox. One way to do that would be to add the feature as a library. So we take the user application, which is written in WebAssembly, and we link it with the platform feature, which would build as a WebAssembly library, and link them together into a combined application with the user application code combined with the platform feature linked into it, making one big WebAssembly module. This has the advantage of putting the platform feature inside the WebAssembly sandbox, which is great. It also gives us the ability to iterate rapidly with the platform features. But it does mean that the platform feature, when it needs to talk to private APIs inside the host, it needs to have access to special private APIs that need to be exposed from the host platform. because there's no isolation between the user application and the platform code. It's just core Wasm, and they're all sharing a single address space. We can't really trust this setup, because we can't really trust that the user application code won't be able to accidentally either corrupt the platform feature's memory or somehow manage to gain access to the private APIs by controlling the platform feature code. So we'd like to have a degree of isolation between the user application code and the platform feature. One family of approaches for doing this kind of thing is to use a microservice architecture. In this configuration, you put the user application in its own service, and you have the platform feature as a separate service, and they talk to each other via a network. This also means that both these features can run inside the WebAssembly sandbox, and they can talk to each other and stay isolated from each other. And they can talk to the host platform via the network as well. But this approach also has some downsides. This means that we have to have a network protocol between all these things. We have to have routing. And we also have to have some kind of way of making sure the user application can't talk to the private APIs over the network. So we have to have some kind of firewall rules or proxy rules, or some kind of configuration to make sure the user application can't talk directly to the private APIs. So instead, we're able to solve this problem with Wasm Components, using a technique called virtual platform layering. If you saw Luke Wagner's talk yesterday, he mentioned this is one of the big advantages of components, and here we're going to use it in practice. So the way it works is we take the user application, and this time we're going to build it as a component. I have this purple box on the outside suggesting that this is an isolated component. And we can link it with the platform feature, which we also build as a component. And it produces a new component, which has the two things inside. Now, there are two things about linking together components that make them very special and different from other kinds of linking. One is that linking components together produces a component. Many times in computing, when we link two things together, we get a different kind of thing. Like we link .o files together and you get a DLL, or you link DLLs together and you get something like a process, or you link processes together and you get something like an orchestration framework. But here, we're going to link two components together, and we'll get a new component. So this is all combined into one file, a single WebAssembly component with the two things on the inside. And the other key property is that when we link two components together, we preserve the isolation. So these two components, when they're linked together, they don't share an address space. They don't have any kind of sharing. There's no namespaces that are shared. There's no kind of shared state. They just remain two independent components that happen to be linked together inside the same container on the outside. And we can use this to implement virtual platform layering. So we take our user application, we link it with the platform feature, we produce this combined result, and now what we have is a component where the user application can talk to public APIs, but only the public APIs. It can't reach the private APIs. And it's directly linked with the platform feature, which can also talk to public APIs, but also has access to the private APIs. So now, because we've preserved isolation, the user application can't get directly to the private APIs. So in a sense, the user application is targeting a virtual platform, the virtual platform being virtually the host platform plus the platform feature. But in practice, by using this kind of linking, we're able to keep the implementation of the platform feature inside the WebAssembly sandbox, where it means isolated from security problems and also from crashing, while giving the user application the impression that it's all running within the same host platform. This is one of the ways that I like to say that the component model really realizes kind of one of the core parts of WebAssembly that goes all the way back to the very beginning. At the very beginning of WebAssembly, one of the things that made it special was the fact that it was able to coexist with JavaScript. WebAssembly code could call JavaScript code, and JavaScript code could call WebAssembly code on the same call stack. In order for this to be possible, we had to be able to say that WebAssembly code couldn't corrupt the stack, couldn't corrupt the JavaScript stack, because this is a browser, and we can't trust the WebAssembly code. That necessitated the introduction of the trusted stack into WebAssembly. And it's that trusted stack that goes all the way back to the very beginning of WebAssembly that we see shining through here in the component model. It's the ability to call from one component into another component without having to have any kind of shared state between the two. It can be crossing an isolation boundary. So at the level of machine code, it's literally just a call. But at the level of security isolation, that call can cross a security boundary. So what we get here is a platform feature that runs inside the WebAssembly sandbox. The platform feature remains isolated from the user application. And the whole thing is combined without any kind of microservice architecture where we'd have linking, or we'd have routing and protocols, and then need to deal with those things. We have linking and calls.
So what does this mean for us practically in terms of implementation? Again, here's today's infrastructure, and here's where we're headed. You can see now that rather than routing your request to the KV store, the KV store logic has been moved to live alongside your application, and then the request is finally routed to our storage routing system. Ultimately, this saves us one extra HTTP hop where we were going from your app via the host platform to KV store, now to the storage routing system. This is cool because now all of the validation, the authentication, caching, and shielding happens basically with your app. No HTTP call needed. In some lab testing, I was able to see about a 3 millisecond overhead with that one HTTP call. And while that might sound small, the KV store's hottest code path is a cached read. And our average time for cached reads is 6 milliseconds. So we're talking about maybe a 50% performance increase here. Pretty huge. The other nice thing is that, as Dan mentioned, previously, if we wanted to ship a new feature, we had to implement the feature in the KV Store Compute app. We had to implement the host calls, and we had to implement the host calls in the SDK. Now that host call implementation has been moved into a separate code base, we no longer have to wait for a full fleet rollout of our changes. My team alone can publish these changes and iterate much faster. Pretty cool.
So to migrate to components in production, we have to figure out what to do with our existing user applications. We want to have a situation where our host platform can run components. So we have to have a way to convert existing user applications, which are using core Wasm, into components. And the way we do this is we've built a special adapter. If you're familiar with the WASI P1 to P2 adapter that exists, that can convert core WASI P1 applications into P2 components, we took that idea and built a larger version of it that has, instead of just the WASI APIs, it has the full FAST API. So we can use that component to link with user applications, which are core Wasm, link it with this adapter, which is on one side the core Wasm API for Fastly user API, and on the other side the canonical API, and we can link the two things together to make a component. So in this way, we can migrate all existing user code to component form. Components basically act like a script, a linker script in some ways. It's a container for inner components, and essentially contains a script for how to instantiate them, how to run them. So when we have an application like this with the outer component that has two inner nested components, the first thing we do is we say, I want to instantiate the outer component. And to do that, the first thing I need to do is instantiate the inner platform feature. So the script says, instantiate the inner platform feature component. And then to do that, we need to instantiate the core module that would be inside the platform feature, because the platform feature itself is a container for a core module. And it uses the imports from the component imports. So it's going to import the host APIs, the private APIs. Once that's done, we can use that to instantiate the user application, because now that's the next component being instantiated, and it can use the exports provided by the platform feature component. And then once that's instantiated, to instantiate that, we can instantiate the core module inside the user application using the exports provided from the platform, as well as the exports provided by the host. So the component essentially acts like a script saying, here's what to do. Instantiate this thing, then use it to instantiate this thing, use it to instantiate this thing. Essentially walks through the process of instantiating core Wasm modules. And one of the key properties here is that this means that from the perspective of the host environment, instantiating a component is essentially using the same logic we already have for instantiating core modules. The way core modules get loaded is exactly the same with components and using core modules directly, because the component is essentially just a script telling the platform, instantiate this core module, and link them together in this way. So it doesn't require any kind of fundamental changes to the way we load and instantiate modules.
So let's talk about the developer experience. How's it going? To see where we're headed, we need to know where we're coming from. This is our actual on-production WIDX and invocation from the SDK. On the left-hand side is how we used to write the bindings for our host calls. We've got three functions here inside of the KV store module: open, lookup, and lookup wait. Open looks pretty normal. It's a function that has one parameter. It takes the name of the store that you're trying to open and returns a result of a store or an error. Lookup is where it starts to get interesting. You can see here that lookup configuration is a pointer to a struct, and handle out is a pointer to a handle. You might recognize handle out as being kind of a C-style paradigm where we pass an out parameter to a function. You can see it in action on the top line inside of the lookup function there. Imagine basically creating a pointer, setting it to null, and we pass it into the function. We check the response from the function for an error, but we still have to check that pointer after the fact down at the bottom here to see if it's still an invalid value. So again, kind of a C-style API. And then lookup weight down on the bottom left takes a couple more pointers. A metadata buffer, the buffer length. We pass in a pointer to a usize where we write from the host call the amount of data written to that buffer. Same thing with generation out and KV error. These are all out parameters. So again, more pointers that we pass into the function, and we have to check on the way out. Because this is just how we return values, multiple values from a WIT_X invocation. But what's this look like in WIT? Here's the new implementation. It's 2 lines of usage on the right-hand side via the glue code, actually, that Luke mentioned yesterday. This is the free glue code that we get generated from WIT bindgen. It just so happens to look exactly like our REST SDK today. This is the same way that you invoke it from a REST SDK, just 2 functions. On the left-hand side, no more Lispy format. We've got a resource here which defines the response from our lookups, and then a bunch of getters on it to read the data that's returned, the metadata generation, and so on. And if we look at the insert here, we get to see something interesting about WIT_X. WIT_X doesn't have optional types, and so if we want to pass in some series of potentially used or unused data fields, we create this down at the bottom left, KV insert config. This is a struct with a few fields that may or may not be used, metadata, TTL, generation. But in addition to passing in this struct, we also have to inform the host call whether these fields are even used. And we do that here with bit flags. So on the right-hand side, you see the SDK. We check whether the user has set this option background fetch. If they have, we set the bit flag. Same thing with TTL. Are they using TTL? Set the bit flag, set the value, and so on. And then again, down at the bottom, you can see another out parameter, pending insert handle out, where we again pass in that invalid value. Then we have to check it after the fact to see if it has indeed been set. And this is what it looks like today with WIT. So right-hand side, boom, again, basically just regular Rust. No optional types here, even though WIT does support them. We just use setters on the resource. If you need to set those values, you just call insert.mode with the mode that you want to use. There are a couple small hitches, though, and maybe you see it just looking at it. It's not quite flawless idiomatic Rust. And that here, you can see the left-hand side, we have a builder paradigm to construct your insert operation. On the right-hand side, we have more of this procedural design. This is because WIT doesn't have a self keyword, so WIT bindgen can't produce this builder pattern. This is mostly to keep compatibility with older languages that don't have the concept, C, assembly, what have you. Another slightly interesting thing is that insert on the right-hand side isn't mutable, but we're calling these functions on it that set new options on the type of request that we're going to make. This is because we don't own the memory to insert at this point. And this isn't a Rust thing. The same is true for if you're using it from Go or from JavaScript. This variable isn't mutable because it's basically a U32 handle to memory owned by the KV store component that we're interfacing with. So the reality of our implementation is going to be that we're going to take this glue code and we're going to wrap it in our SDK. The big gain here is that we're taking an SDK that's probably about 1,000 lines today and making it just 100 lines of a thin wrapper around the glue code that's automatically generated from WIT bindgen. So overall, excellent developer experience. Love it. WIT's amazing. Never going back to WIT_X. unless my boss asks me to.
One additional piece of this puzzle is distributed components and WIT interfaces. And to do this, we can use the Wasm OCI artifact layout, which is a defined layout for storing Wasm in OCI registries. In addition to Wasm components and modules, we can also store WIT interfaces. There's a binary format for WIT interfaces to store in this registry as well. And so this is a way we can use to distribute WIT files between projects to make sure we have the same WIT file in the producer and the consumer. And using this registry, we can also make sure this is a way we can distribute components to have the components for things like the platform features available in the registries. We can pull them down when we're ready to link them into the user application. This allows us, using the OCI registry, allows us to use existing OCI registry infrastructure. So we don't need to have a new service for having a new registry. We can use existing OCI registries, such as GHCR and GitHub. And that's an edge KV store built with Wasm Components.
Looks like we've got some time for questions. One over here.
What's the timeline for everything else in the Fastly compute space moving over to Wasm Components?
As soon as we can. I don't have a real answer for that. There were a lot of prerequisites for getting this running. We're still working on a lot of it. Yeah, I don't think we have an official date, but I know that a lot of people inside of Fastly are excited not just to use the new technology, because there's real-world gains to be had here. So we're excited about it. I don't think there's anything barring it, except from like the fact that we just need to do it. Cool. All right. Thanks, everybody.
Thank you.